Over 80% of all stuff in the universe is composed of materials that scientists have never observed before. It's called dark matter, and we only assume it exists because the behavior of stars, planets, and galaxies would be senseless without it. Dark matter is one of the few substances in space that both scientists and the general public find surprising. One of the characteristics of dark matter is frightening because it is absolutely undetectable. It doesn't emit, reflect, or absorb electromagnetic radiation like X-rays or radio waves, so it cannot be detected by standard sensors and detectors. Scientists believe that the secret to its enigmatic character lies in its composition. We're ready to learn more about it thanks to the new James Webb Space Telescope. Join us as we explore the James Webb Space Telescope's game-changing discovery of dark matter. What is dark matter exactly, and why is it the stuff of nightmares in space? Dark matter is a component of the universe whose existence is determined by gravitational attraction rather than brightness. Dark matter accounts for 30.1% of the universe's matter-energy composition. The rest is dark energy and ordinary visible matter. The simplest method to understand dark matter is to contemplate what it isn't. Therefore, we'll take that approach to completely comprehend this concept. As common as atoms are assumed to be, they only account for around 5% of the universe, according to a cosmological model known as the lambda-cold dark matter model, also known as the Standard Model. Furthermore, other than the fact that they both have the label dark matter and dark energy are different. According to the Standard Model, dark energy accounts for about 69.4% of the universe. The existence of dark matter was initially suggested by Swiss-American astronomer Fritz Zwicky, who discovered in 1933 that the mass of all the stars in the Coma cluster of galaxies contributed just approximately 1% of the mass required to keep the galaxies from escaping the cluster's gravitational pull. The existence of this missing mass was questioned for decades until the 1970s, when American astronomers Vera Rubin and W. Kent Ford observed a similar phenomenon. The mass of the stars visible within a typical galaxy is only about 10% of that required to keep those stars orbiting the galaxy's center. In general, the speed with which stars circle the center of their galaxy is independent of their distance from the center. Moreover, orbital velocity is either constant or slightly rises with distance rather than decreasing as predicted. To account for this, the mass of the galaxy inside the star's orbits must rise linearly with the star's distance from the galaxy's center. This interior mass, however, emits no light, thus the name dark matter. Since the discovery of dark matter's existence, a preponderance of dark matter in galaxies and clusters of galaxies has been discerned through the phenomenon of gravitational lensing, matter acting as a lens by bending space and distorting the passage of background light. The motion and heat of gas that gives rise to observed X-rays have also been used to infer the existence of this missing matter in the centers of galaxies and clusters of galaxies. The Chandra X-ray Observatory, for example, observed that in the Bullet cluster, which is made up of two merging galaxy clusters, the hot gas is slowed by the drag effect of one cluster passing through the other. The mass of the clusters, on the other hand, remains unaffected, indicating that most of the mass consists of dark matter. Matter accounts for 30.6% of the universe's matter-energy composition. Only 0.5% of the stuff in the universe is in the form of stars, and 0.03% is in the form of elements heavier than hydrogen. The rest is dark matter. There are two types of dark matter discovered. The first kind accounts for around 4.5% of the universe and is composed of the familiar baryons, which also comprise the luminous stars and galaxies. The majority of this baryonic dark matter is believed to exist in the form of gas in and between galaxies. By measuring the abundance of elements heavier than hydrogen that were created in the first few minutes after the Big Bang happened 13.8 billion years ago, it has been possible to identify this baryonic, or ordinary, component of dark matter. The remaining 26.1% of the universe's mass, known as dark matter, is in an unidentified, non-baryonic form. The rate at which galaxies and massive structures made of galaxies coalesced from density fluctuations in the early universe suggests that the non-baryonic dark matter is relatively cold, or non-relativistic, meaning that the cores of galaxies and clusters of galaxies are composed of heavy, slow-moving particles. These particles are electromagnetically neutral since there is no light coming from them. Weakly interacting large particles is the term given to the particles as a result of these characteristics. The precise nature of these particles is still unknown, and the Standard Model of particle physics does not predict them. But other potential extensions to the Standard Model, such supersymmetric theories, predict hypothetical elementary particles like actions or neutralinos that may be the undiscovered WIMPs. Unusual attempts are being made to detect and measure the characteristics of these unseen WIMPs, either by watching their impact in a lab detector or by watching their annihilations after colliding with one another. There is also some hope that tests at cutting-edge particle accelerators like the Large Hadron Collider may reveal their existence and mass. Gravitational changes have been suggested as an alternative to dark matter to explain the apparent existence of missing matter. These modifications imply that ordinary matter may exert a stronger attractive force under conditions that only exist on a galactic scale. However, since they provide little or no explanation for the modification of gravity, the majority of the solutions are unsatisfactory on theoretical grounds. Additionally, these theories are unable to account for the finding that dark matter and regular matter are physically separated in the bullet cluster. This division shows that dark matter can be distinguished from regular matter and is a physical reality. How do scientists study dark matter? Astronomers may detect dark matter by measuring the amount of mass in stars and galaxies. For example, many galaxies could not exist or move as they do without a sufficient amount of invisible mass to assist astronomers in detecting their dark matter, which is part of the primary evidence for dark matter distance. More specifically, the James Webb Telescope will take incredibly sharp pictures that will enable researchers to spot disruptions caused by gravitational lensing, pointing them to the site of the hidden mass. When a light beam travels through a massive mass, it is somewhat deflected because the object warps the fabric of space-time. The James Webb Telescope can detect these masses and determine what is missing or not viewable by photographing distant galaxies. This is most likely dark matter. This kind of measurement is ideal for the upcoming Space Telescope. Because of its incredibly sharp images, relatively little disturbances may be measured. The Space Observation Station has access to a lot more background galaxies to assess disturbances brought on by this gravitational lensing phenomena, since it can look so far into space. The amount and composition of dark matter in galaxies may then be estimated by scientists by comparing these facts to theories about how it works in the universe. The James Webb Space Telescope will also collect a variety of galaxy evolution data. The James Webb Telescope, which will cost $10 billion, will enable us to explore deeper into space and further into the past than ever before. The JWST has been successfully delivered to its permanent location, and scientists are eager to use it to study dark matter. The Space Telescope will investigate the origins of the universe and its galaxies, as well as the role that dark matter may have played in their evolution. By making these observations so far into space, it was successful after a nerve-wracking launch that required the most delicate components to be folded up in order to fit the large size of the telescope on the launch vehicle. The delicate but wide heat shield that would protect the infrared instruments from heat interference, for example, as well as the 6.3-meter wide mirror that is divided into 18 separate hexagonal segments had to be folded. Both components started to unfold in space as the JWST traveled to its ultimate destination, which is around 1 million kilometers from where it would circle the Sun. NASA had to ensure that everything was in order since there was only one opportunity to get it right before the launch. The telescope is so far away that sending a repair mission to it in its permanent position is impossible. Even refueling is uncertain, while NASA is willing to investigate the idea given that the propellant in the JWST can last for about 2 decades. Originally expected to last for 10 years, a successful deployment has made it possible for enough fuel to extend the mission by 2 decades. Currently, NASA is calibrating and setting up the JWST, aligning the 18 mirrors to provide coordinated images rather than individual ones. The JWST will begin shooting stunning pictures of the universe in a few months. One of the scientists eager to use the JWST is Professor Matthew Walker of Carnegie Mellon University, who is the lead researcher of a project that will use information obtained during the telescope's first year of mission. He's going to work on dark matter, but with a new approach known as dark matter theory. The dark matter theory predicts that rather than agglomerations the size of galaxies, dark matter would be discovered in tiny basic units known as halos. There is now something to keep in mind with the JWST, which we will quickly discuss below. The telescope is designed to be an infrared telescope capable of observing the past and outer reaches of the cosmos. Walker and his colleagues will examine very fragile gravitational systems for disturbances caused by subgalactic dark matter halos. The characteristics you want in a narrow field of view instrument are those that enable you to examine individual objects in great detail. However, while investigating dark matter and dark energy, you might have more success. Dark energy telescopes attempt to investigate a vast area of the sky in order to learn about and quantify this phenomena. To learn about and quantify it, we add up its impacts across a vast region or volume. In contrast, the Nancy Grace Roman telescope, which is set to launch in 2027, will have a broad field of view that will allow it to scan enormous swaths of the sky, which is exactly what is necessary to assess the impacts of mysterious forces on key structures or parts of the cosmos. While Nancy Grace Roman may be able to locate hundreds of distant supernovae, it will be the JWST's task to make the most accurate measurements of those distant lampposts possible. We will keep you updated on new Nancy Grace Telescope and new discoveries of JWST. Stay tuned for more epic content like this. We'd love to hear what you think about the dark matter and JWST in the comments section below. And thanks for watching the video. If you want to continue to learn about everything regarding incredible things, we've got 2 more video options for you on the screen to check out. And don't forget to give a thumbs up on this video if you liked it and subscribe to the Electric World channel. We upload some pretty awesome stuff here which you will most certainly enjoy. Hit a like on this video and leave a comment below. See you guys in the next one.